Okay, so it's a pleasure introduce Anita, our new colleague here at the observatory. Anita recently moved to Bologna from another institute, another INAF institute from Padova. She obtained her PhD a few years ago in Paris, in Saclay, after which she spent some years as a postdoc at ISO in both Gassing and Chile, right? Or not? Okay. Correct me if I'm wrong, because I don't have everything under control. And recently she obtained, she applied for a relocation, let's say, and she joined us at the INAF Institute, and so today she's going to introduce herself explaining us her most important research fields, the topics which she works the most. Okay, so see you later. We'll take questions later. Okay.
Good morning, everyone, and thanks, Francesco, for the introduction. Yes, maybe not. Yes. Yes, so I will take the opportunity of this JAC to introduce myself and some of the research fields I'm working on since I recently moved. And so today I decided to talk about two of the things that are fascinating me lately in astronomy. One is the search for gas and more in general galaxy formation, galaxy evolution. And the second one is the use of sound to represent astronomical data. And the reason why I decided to put together these two topics, which are really different and I would say almost orthogonal in the same talk, is that because I'm feeling more and more like Dr. Jekyll and Mr. Hyde. Some of you know Dr. Jekyll, who studies galaxies, and others know Mr. Hyde, who uses sound to represent data. So, okay, now today I have the occasion to reveal that I'm both Dr. Jekyll and Mr. Hyde. And I mean, the talk will be divided a bit in these two parts and give highlights on these two topics. So I will start with discussing galaxies, and in particular, the search for molecular gas of galaxies, both star-forming and passive, at high redshift. So just to set the stage a bit, there is, I would say, in the community a general consensus on the fact that the majority of star-forming galaxies, at least up to redshift 6, assemble their mass through secular processes. And this is shown by the fact that galaxies obey some scaling relations, and among them, the main sequence and the Schmidt-Kennicutt are the two that I'm going to discuss. So the main sequence is shown here. It relates the star formation rate of galaxies with their stellar mass. The normalization of the main sequence, increases with increasing redshift, but its slope remains almost constant at all redshifts. And something similar happens for the Schmidt-Kennicutt plane, which instead relates the star formation rate surface density with the molecular gas surface density. And when we go to higher redshift, galaxies become denser and denser in both parameters, but they still lie along the same relation as the local ones, which has basically a slope of 1. So this means the galaxies are, in general, in dynamical equilibrium, but there are also deviations from this equilibrium, which are mainly represented by starburst and quiescent galaxies. And so these deviations from the equilibrium open big questions such as, why do galaxies suddenly ignite the formation of thousands of stars per year and become starbursting? And also on the opposite, why do they stop forming stars and become quiescent? And these two questions might actually be linked. So it is possible that galaxies that are on the main sequence go through gas-rich mergers or gas accretion from the cosmic web. So they become gas-rich, they start forming a bunch of stars, they become star-bursting, and then either the gas is consumed or expelled or just stabilized, and then star formation is quenched and it drops and galaxies become quiescent. So as you might have understood, the key ingredient in all this game is molecular gas, which is the fuel for star formation. And this is what I'm going to focus on now. However, funnily enough, molecular gas, so H2, is difficult to observe in the local universe and it's not observable at high redshift because we don't have the instrumentation to do so. So what we need to do is to find proxies, so other tracers that are telling us how much molecular gas is there in galaxies. And the traditional ones are the CO, which is a line emission, and dust continuum. They all have pros and cons, but in most recent years, many other tracers of molecular gas. Let's do, because I don't see the cursor anymore. So let's see if I can stop sharing. Click and share again. Yes, good, thanks. So many other molecular gas tracers have been proposed in recent years. Among them, C1 seems to be really a good tracer, although it's quite faint, so difficult to observe at high redshift. C2 is very bright, so it's very convenient at high redshift, although some limitations might be the fact that it doesn't only trace the molecular gas, but it can trace all gas phases. And then pH is some of the most recent tracers that have been proposed. So many tracers are available, all have some limitations and some advantages. I would say we can pick the one we prefer, keeping in mind what the limitations are. And this enables us to start and look at what are the properties of galaxies in terms of molecular gas content and characteristics. So in particular, what we can do is to see what is the cosmic evolution of the molecular gas density that is shown in this plot. So the molecular gas density seems to increase from redshift 0 up to cosmic noon, redshift 1 to 2, and then to smoothly decrease at higher redshift. So the squares represent observations. Many of them have been carried on by Roberto, and then there are the models, which are broadly in agreement with the observations by now. And this evolution of the molecular gas is very similar to the evolution of the star formation rate density, again, strengthening what is the link between star formation and molecular gas. However, in that plot, each galaxy is an integrated data point. So we are considering what is the bulk of the molecular gas in each galaxy. Now that the resolution and the sensitivity of the instruments are improving, what we can also start doing is to resolve individual galaxies and look at the detailed properties. And so, for example, this enables us to look at the morphological properties of galaxies. So we already know from optical data that the morphology of galaxies at high redshift is quite different with respect to the local ones. Local star-forming galaxies mostly have these spiral shapes with a central bulge. They form stars in star clusters and star complexes, which are which are created in giant molecular clouds. At high redshift, the morphology is a bit different. Galaxies are mainly irregular, and they have these bright knots of star formation, which are typically called clumps. In the field, the clumps seem to be quite massive and large. They have sizes of hundreds of parsec up to kiloparsec. But when we start to observe star-forming galaxies which are lensed, as the ones that are shown here, then we are able actually to resolve the individual clumps and to see that they're made of star complexes, stellar complexes, and even star clusters in the most magnified cases like these ones. And I mean, this is a research line that Eros, Matteo, and Francesco, we are working on that. But today I promised to talk about molecular gas, so I'm not really discussing this example. I'm rather focusing on the search of molecular gas in these clumps. So they're young, they're actively star forming. We were expecting to easily find some molecular gas that is fueling the star formation. However, it was not that easy. So if the clumps are formed in situ in the disk of galaxies that are gas-rich, gas should be there. And so we took one of the prototypical clumpy galaxies at cosmic noon and observed with ALMA. So the crosses, okay, this is an enlarged version. The crosses indicate the location of the optical UV and optical clumps. And as you can see, there's no CO at all at that location. That CO is all concentrated in this region, which has redder colors, and is probably overlapped with a forming protobulge. So maybe in this case, the resolution, the sensitivity was not enough to detect the clumps. However, in parallel, other groups started to observe sub-millimeter galaxies. So galaxies that are very bright at sub-millimeter wavelengths and they are lensed. So we should overcome the problem of the resolution and the sensitivity. They were observed in dust continuum, in situ emission, both probing molecular gas. But again, no clumps were there. However, in these cases, no UV or optical images were available. So maybe these galaxies were not clumpy in the first place. And that's the reason why giant molecular clouds were not found there. Another reason could be the short timescale for star formation. So the gas might have been turned into stars very quickly or expelled, and so no molecular gas is available anymore in those star-forming regions. Finally, in recent years, Mirka de Soljavatsky and their group started to find some detections of CO in lensed galaxies at redshift 1. So here in the background, you see the optical images of these two lensed galaxies, and the contours show the CO emission. So they compared the molecular clouds at redshift 1, which are these colorful points, with the local ones. They compared the molecular gas content and the size. And it seems that at high redshift, giant molecular clouds are denser and have higher internal pressure than the local ones. So star formation might happen in environments and conditions that are a bit different at higher redshift than in the local universe. Of course, they reached redshift 1. Why not pushing higher redshift? And that's what we tried to do with another lensed galaxy at redshift, this time 3.5, so a bit higher. We changed the tracer. We took C+, which is bright and therefore convenient for this game. These are two images of the same galaxy, and we detected the C+. Interestingly, one of the clumps has both UV and C+ emission, so star formation and molecular gas at the same time. Whereas we also discovered two clumps that only have the C+, no UV, so only molecular gas. If we place them in the Schmidt-Kennicat plane that I've shown at the beginning, we find that the clump that is detected both in UV and C2 is up there. So it has an extremely short depletion time, whereas the other two have depletion times that are more similar to the redshift 1 GMCs. So probably a very intense star formation episode as a little starburst is going on in this region up there, whereas in the other ones that are only detected in C2, we might be probing the onset of star formation. So the star formation didn't start yet or just started. It's not visible in the UV yet, but we just see the molecular cloud that is forming it. So I would say different depletion times are really probing different phases in the lifetime, let's say, of molecular clouds and star-forming regions. And multiple tracers are key to really probe their evolution and to probe their star formation cycle. The next thing we can do, apart from morphology, once we have resolved gas measurements and data with good spatial resolution and sensitivity, is to measure the dynamics of galaxies. And big efforts have been put into this game. So, for example, there have been several ALMA large programs, the Crystal program, a redshift between 4 and 6, and more recently, the Condor large program that has been led by Francesca Rizzo, which is probing CO in main sequence galaxies, a redshift 1 to 2, in an homogeneous sample. So this sample will allow us, we are just getting the data, it will allow us to probe not only the morphology, but also the dynamics of galaxies. And so to create velocity maps like these ones and velocity dispersion maps, and to estimate what is the turbulence of galaxies at cosmic noon. Until now, this game, it was very difficult to play this game because we were missing the cold gas tracers. So the turbulence of galaxies at high redshift was mainly inferred from H alpha, so optical lines. And from these optical lines, the community was finding that velocity dispersion of galaxies is increasing from redshift 0 up to redshift 2, and then it reaches a sort of plateau above redshift 2. And the V over sigma, the ratio between the velocity and velocity dispersion, follows a similar trend, but in the opposite direction. So these measurements were done with H alpha. Recently, we could measure the same quantities, but using CO, C1, C+, so molecular gas, the cold gas tracers. And what we find is that actually the velocity dispersion is 3 times lower than the one measured with H-alpha. So H-alpha is the black line, and the pink lines indicate the fit of the points, which are the molecular gas tracers. So this indicates that the disks are colder at high redshift than it was previously expected, and are more similar to the local ones. And also, this means that the H-alpha measurements are not only probing the turbulence of the gas, of the thin disk of the gas, but also non-circular motions like outflows and other kind of motions that are biasing the measurement. And this conclusion is also reached by hydrodynamical simulations. These are the Sala simulations, where both C2 data and the H-alpha data are available. So the C2 are the blue curves, the H-alpha are the red curves. And also in this case, the C2 is really tracing the thin disk where the molecular gas is settled, whereas the H-alpha is rather tracing also the outflows and the other motions. This has implications on the star formation models that we are using. So for example, right now, to explain the velocity dispersion that is observed at high redshift, we just need stellar feedback. That's enough to reproduce it. Whereas earlier times, when the H-alpha measurements were considered, gravitational instabilities were needed to explain the high turbulence at high redshift. And gravitational instabilities were also used to explain the formation of these giant clumps. So changing these models of star formation really has implications also on the morphological conclusions that we are having. So it is still challenging, but okay, we now managed to detect molecular gas at high redshift, especially in a spatially resolved way to measure the kinematics. The question remains, what about passive galaxies? So we would expect non-detections because there are several mechanisms explaining the quenching of star formation with gas removal. So the gas is just removed from the galaxies because of AGN or stellar feedback, because of run pressure when galaxies fall into galaxy clusters, or strangulation, starvation. So the gas is prevented to fall onto the galaxies from the cosmic web. However, there are some scenarios that also predict that the molecular gas is still there to some extent in passive galaxies, but it's just prevented to form new stars, to collapse and form giant molecular clouds and therefore stars. So the gas is just stabilized or heated. It's too excited to collapse and form these new stars. So to understand what are the quenching mechanisms in different cases, what we can do is to, let's say, catch galaxies while they're quenching and investigate what is their molecular gas content and conditions. So one key population to play this game are post-starbust galaxies. These are galaxies on their way to become quiescent. They have these peculiar spectra with deep Balmer lines and little or no nebular lines. They have prominent bulges, and often they have disturbed morphologies that remind of recent mergers. And they also have colors that place them in the green valley. So they're transitioning from the main sequence to the quiescent region. Also in the main sequence that I've shown you before, the post-starbust galaxies are in between main sequence and quiescent galaxies. In the local universe, there were hints that these post-starbust populations were still retaining some molecular gas. So we tried to push observations to higher redshift. We arrived to redshift 1. And it seems that post-starbust galaxies have non-negligible gas content. So they have gas fractions between 8 and 16%. So here the vertical axis is gas fraction and redshift on the x-axis. And the post-starbust are here in between the main sequence and quiescent galaxies. Okay, there are also some post-starbust that have very low gas fractions, but I'm not going to discuss them now, and this might be related to their very high stellar mass. What appears from the, again, mechanical plane is that the post-starbust have decreased star formation rate with respect to main sequence, which are lying along this line, but they still retain substantial molecular gas. So this is pointing towards quenching mechanisms that do not remove the gas completely, but rather stabilize it or heat them up. And one of the key players here might be mergers. So in some of these galaxies, we found nearby companions that are very gas-rich, for example, in this case. And this is also in agreement with literature results that find some of these prostarbars to have merger features and merger remnants. So the mergers might be either stabilizing or heating up the gas, stopping star formation, and then other mechanisms might be in place at later times to remove the gas and keep the galaxy quiescent. So we were looking for molecular gas in star-forming regions where we expected to find it, and it was really hard to find it. We looked for molecular gas in passive galaxies where we expected very little, and we found it. My conclusion is that reality is quite surprising and much more complex than what appears at first glance, especially if we don't see what we study. And here, Mr. Hyde is coming back, in the sense that none of these data that we are taking are actually visible. We get numbers, we translate them into plots and images, we stare at them, and we reach conclusions. Or at least we explore them and we reach some conclusions. So we are used to think, and here the second part starts, we are used to think that astronomy is a visual science. But is it really the case? I mean, telescopes collect light, we use visualization tools to explore data, and we present the public with beautiful images. However, this has several limitations, and among them, the fact that we limit astronomy exploration to a monosensory exploration, whereas we explore reality with 5 senses usually. And also, this means that astronomy is not accessible to blind or visually impaired people. But there is no reason for that, because I would claim that we are all basically blind to the universe. We need telescopes to see beyond the closest 1,000 stars. And the visible light is just a tiny fraction of the electromagnetic spectrum. Most of it, in general, what we get from telescopes are numbers that we are used to turn into images. So here, what I want to claim is that I think there is a huge potential to use multisensory approaches for astronomy research and outreach. And this benefits everyone. And it also has the advantage that makes science accessible for everyone. So when I talk about, well, one of the ways of making astronomy and science in general multisensory is to not only use visualization, but use sonification, so use sound. And when I think about sound, I think about non-speech audio, so non-vocal audio. So there are 2 ways of turning data into sound. One is the so-called audification. So we directly turn the data point into a sound. And this is what the doctor does when he uses the endoscope to listen our lungs, for example, or the Geiger counter that clicks every time a particle hits it. There is also an indirect way to turn data into sound, which is called sonification. So in this case, we map physical parameters, for example, luminosity, into sound parameters, for example, pitch. This is arbitrary, it's a choice, and it is as arbitrary as turning data, for example, luminosity, into visual quantities like colors. We just change the sense that we are using. And I would say there are several benefits of using sound. So I'm not claiming to replace visuals with sound. I'm just suggesting to enhance visuals with sound. And one of the benefits, for example, is the fact that sound is naturally multidimensional. It has 12 dimensions, whereas visualization, well, we can visualize at most 3 dimensions. More becomes challenging. But we have more and more as researchers to deal with big data and big data cubes. So we need to prioritize what is the information to visualize. What we could do is to use sound to explore some of the dimensions. And I would like to present an example. So there was this team of physicists that had to compare 2 big data sets, which are, one visualization is shown here. And they claim that the 2 data sets were the same. a sound designer, Stephen Barras, arrived and he took the two data sets and transformed them into two objects that can actually produce sound, which are these two bells. So now I will let you listen how the two bells sound. First, the first data set, and then the second one. Okay, I'll play it once more. And the question is, do they sound the same or do they sound different? Different. So the data sets are different, but visually they seem the same. So there was actually a long discussion between the physicist and the sound designer. And in the end, the physicist went into different visualization and they found that one parameter was actually different. So this is a case, maybe an extreme one, I don't know, but this is showing that sometimes sound might be helpful into exploring some of the multiple parameters that we have to deal with. Another example is the fact that most of us, I think, spend their days looking at tiny, faint signals in the noise. And sometimes it's difficult to detect this signal. But the ears are naturally very prone to detect, to listen, to perceive several sounds simultaneously, filter them, and just hear what we're interested in. This is called the cocktail party effect. So if we are in a noisy room, we can hear the sound, the voice of our friend, and understand what he or she is saying in the noise. So we could use this natural feature of our hearing system to detect signals in noisy data sets. So this is an example taken from the gravitational wave domain. The plot on the top is strain as a function of time. These are two black holes that are merging. It's a simulation. And I will let you listen to the sonification of this model. Okay, remember it, because then it was put, the model was put into actual data from LIGO, which is the bottom plot. It's very difficult where the signal is visually, at least for me. But if we listen attentively to this data set, I think it's easier to detect it. So to understand when the merger of the black holes is happening in this sequence. I can play it again. Okay. It's easier with the headphones and the good system. However, once you hear it, you can also a bit see it. It's here halfway through the sequence. So again, in this case, listening to the data might help discovery. And the last point is that the ear is better than the eyes at perceiving time-based information. So for example, the rhythm that we can remember very easily and that is always active. So we don't need to stare at the screen to listen what is happening. And this might be helpful to, for example, listen to transient events or rapid events. And this is an example that was actually used to identify some radio bursts at an observatory and then quickly followed them up. Okay, so it might not be very pleasant to hear these things, but it might be helpful. And despite these benefits, sonification is still very niche, it's still at the beginning. And the main reasons why it is not widely used is the fact that we lack training, standards, evaluation, proper dissemination. We don't know that this is a possibility, and so on. So I started recently collaborating with an international team of astronomers that are interested in the topic, psychologists working on psychoacoustics, musicians, educators, trying to understand how can we improve, evaluate, and create standards for this. We actually discovered that there are many sonification projects that apply to astronomy. The first one dates back in 1960, when it was actually used to understand something that, if you want, we can discuss later, about space missions. So it was used with a research purpose. It was not outreach. And since then, many new projects start to appear every year, between 10 and 20 projects per year. Most of them have public engagement as the main goal, but I would say an important fraction, 25% of them, have research as the main goal. And accessibility in most cases is a secondary goal. So we started to evaluate what is the effectiveness of sonification for research. Is it effective? Does it work or not? And so with a PhD student in psychology, we started to run experiments. We simulated light curves from exoplanet transits. So when the planet passes in front of a star, we have a dip in luminosity, in brightness. This is the visualization of the light curve. And we translated the flux into pitch in the first case, or into the duration of the sound in the second case. And we also use multiple stimuli, so pitch plus duration. So you can see the visualization. I will let you listen first to the pitch sonification. So the transit will happen when the pitch increases. Okay, quite easy to detect. The same for the duration. The duration is longer in the transit. Okay, we compared astronomers and non-astronomers and their performances when using visualization, which are the yellow points, or sonification, which are the other points. So clearly, visualizations outperform the sonification. We are a lot more effective in detecting transits visually. However, what is interesting to me is the fact that the astronomers are doing much better than the non-astronomers at any signal-to-noise ratio. And I think that the reason for that is training. We are trained to look at plots and data, and so we are very effective in finding features visually. But we might also start training people to listen attentively, and then sonifications, the performances in sonification might increase. And this is one more recent experiment that we're carrying on the effectiveness of training, how to do it, and how effective that is. The other thing that I found interesting is that we were computing the so-called response bias. So how much people are prone to say, yes, there is a transit, or no, there is no transit, using the different stimuli. So the dotted line is no bias. What I find interesting is the low signal-to-noise regime, where both astronomers and non-astronomers have a big bias saying, no, there is no transit when using visual data, even if the transit is there. That is, the bias is a lot milder when using sonification. So we might miss some important, some signals or some detections when inspecting the data visually, just because we are extremely conservative when we do so. And this case might not be there when we use sonification. Of course, sonification, and I'm almost done, has also several advantages for public engagement and education in the schools. Accessibility is one of the main ones, but it's also very interactive and curious for the public. And we are now starting to use sonification in this project that I'm leading. Again, it's an interdisciplinary project. It's called the MACA, Astronomy Education with a Multisensory, Accessible, and Circular Approach. We use the approach of the universal design for learning. That means to create equal opportunity to learn for everyone, irrespective of disabilities. What we do is to create educational resources which are multisensory, multidisciplinary, interactive, and multicultural. So we started in Italy. We are expanding now a bit abroad, mainly in the Mediterranean area. All the resources are publicly available. They're on these websites. And we use several tools. I'm just showing one because I think it's fun. It's a software that Michele Ginolfi and Luca Di Mascolo have been developing recently. I was testing it with school kids. So it is called Derakoi, and it allows you to listen what is the color of the pixels of an image by just scrolling your hand in front of the image. So this is a video that might be clearer than my words. Okay, there are several sounds that you can use, more pleasant ones, less pleasant ones. We tested them in geometry classes and science classes in schools, and asked the kids to identify colors and shapes without seeing the images, just listening to the sounds. And this seems to be quite encouraging. But okay, I will not show you the results now, just for the sake of time. Amaka goes through a long, let's say, it's an educational path, and some of the PhD students here know because they were involved at some point. So we ran a course for PhD students, sometimes in Bologna, sometimes in Padova. This year is in Padova, just because I just moved here. And so we guide the students to convert a scientific idea to transform it into an educational or a public engagement activity that is multisensory. We do it in collaboration with the Association for the Blind and the Association for the Deaf. And then PhD students train about 60 high school students every year about how to deliver the activity and handle the public. And the high school students run the activities during an astronomy festival that we organize every year near Mantova, which is called the University Node Senses. In the fall, we have a teacher training program to teach teachers about these activities and bring them back into the schools. So we are just starting the 5th year of activities with Amaka, and during the first years, we reached about 17,000 beneficiaries. And of course, every year, this number increases a bit. So I take the occasion to invite you to the next festival, which is in June, 6, 7, 8 of June. Every year we have a theme. This year, the theme is darkness. There are these interactive workshops that I've just described, but also exhibitions, conferences, shows, observations, and many other things. You can find more information on the website, on the social. I would say Amaka and the festival attracted quite the attention on internationally. There have been several articles, and here there are QR codes in case you're interested to read some of them. But I think at the moment I would stop here and take questions if any.
Thank you very much, Anita, for the interesting double experience.